All right, kids, this is just the review. It's going to be notes number 59 to the end. I think it's 74, 75. This is in the notes, so we'll just keep going. Question 59 says, a physical change is another way to say what? When you have a physical change, does a compound form? Does a phase change form? Does matter turn into something other matter? Or do you change the shape by squishing it or pushing the matter? A phase change is a physical change. Phase changes are physical changes. Match these up. You got gases, liquids, and solids. Now, one of them, gases, is going to have either definite shape, definite volume, blah, 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 red, green, or blue. Take a moment, use your pencil, see if you could figure these out. I'm going to do the answer now. If you're not ready, hit pause, but here goes. The gas has an indefinite shape. Takes any shape of container, you put it in, and it also has indefinite volume. You can squish it or you can let it expand. It'll get more concentrated if you squish it. It'll get less concentrated if you make it big. Liquids are blue here. That means they have any shape. They'll take the shape of any container. You put them in on the bottom, but they do have a definite volume. You can't squish them. And solids here are red. Solids, of course, have a definite shape. The shape does not conform to the container you put them in. They hold their shape, and they have a definite volume. They can't be squished. What does this crazy big word mean? The big H word, heterogeneous. Heterogeneous means not the same throughout, like Raisin Bran cereal with milk or sand and water in this case. The sand sinks, and I guess there's a little bit of sand still floating in that water, but it'll all settle out. It's not the same throughout. Not the same throughout. There's an old Regents question. This is a great one because it's really just a sort of a twist on the letters. You got to be paying attention. It says, which can be decomposed by a chemical change. In order to be decomposed, that means to come apart, you have to have parts. A is this symbol CO. That's an element. It's called cobalt. You can have a chunk of cobalt. You could have two chunks of cobalt, but cobalt is cobalt. C, Hg, is my favorite element, mercury. You could have a cup of mercury. You could have 2 little cups of mercury. You could have 17 little tiny drops of mercury, but you can't change it chemically. D is iron. You can have a hunk of iron. You can have a bunch of little hunks of iron, but iron is iron. But B, choice B, look at that formula, CO with a capital O. Not like the A, C little o. This is C big O, capital. C is for carbon. O is for oxygen. This stuff is called carbon monoxide as opposed to carbon dioxide that has 2 oxygens. This is carbon with 1 oxygen, carbon monoxide. That one can be broken down into carbon and oxygen. That can be decomposed by a chemical change into simpler things. It's a compound. You can unbond it into carbon and oxygen. How could you separate a mixture of salt and water, salty water? Could you do chemistry on it? Can you filter the salt out? Can you use a magnet, or can you distill it? As you remember, we separate mixtures by taking advantage of a difference in their physical properties. Number one, it's a mixture. It's not a chemical compound, so you don't have to do chemistry to it. A is wrong. Mixtures are physical blends. They need to be physically separated, not chemically. Salt and water. Salt particles are just as small as water molecules. When they go through the filter, they go through the filter. You can filter salt water, and what do you get on the other side? Salt water. Filters are not small and fine enough to take the salt out of the water. Magnets work really well if one of the parts of the mixture are magnetically attracted. Salt nor water are attracted to magnets. So you could stir all day long with a magnet and not going to take anything apart, not salty water. But with the distillation apparatus, you can take advantage of a difference in the boiling points, right? Salt and water boil at different temperatures. Water boils at about 100, and the salt would boil at about 4,000. So if you heat it up to the salty water to say 105 degrees centigrade, the water would boil off. You could distill it and catch it and condense it into some water in a beaker on the other side, but the salt would just get hot in the distillation flask. So you could take advantage of a difference in boiling point. Convert the melting point of copper into centigrade degrees. Use the formula. What formula are we going to use? K equals C plus 273. So you write the formula. K equals C plus 273. You go to table S. Got it right here. Gotta have it handy. Copper, element number 29. The melting point, 1358 Kelvin. 1358 Kelvin equals C plus 273. We subtract 273 from both sides, and the centigrade temperature for the melting point of copper is right there. These are easy. You got to write a formula. You got to put the numbers in the right place, though. All right, 502 grams of iron completely combines with 216 grams of oxygen to form rust. How many grams of rust form? Don't make this a big deal. Iron and oxygen make rust. Iron mass plus oxygen mass makes rust mass. The mass of the reactants equals the mass of the products because of the law of conservation of matter. Matter can't be created or destroyed in a chemical reaction or in a physical change. This is a chemical reaction. Iron and oxygen chemically form into a new compound called rust, or iron Roman numeral trioxide, and it's just a simple math problem. 502 plus 216 gives you a total of 718 grams of rust. Perfect mathematics. The reactant mass equals the product mass. When two elements chemically combine into a product, what's the product? Does it have the same properties as the reactants? Is it a blend, like an average properties? Does it have new unique properties that's unlike the reactants? Or may or may not be similar, depends on what the elements are that are combining. This is a good question. Think about it. Hydrogen and oxygen make water. Hydrogen and oxygen both explode. You can breathe oxygen. Hydrogen's a gas, you can breathe it in and out, but you're not gonna live if you just breathe hydrogen. Water is totally different. Water's got all new properties. Water's unlike hydrogen or oxygen. When a chemical reaction occurs, new unique properties in a new substance. Not the same, not an average, not a mixer, completely different. New stuff forms with new properties. Count the number of atoms. Now, you don't have to know these names. We'll learn about them another day. First one's called aluminum permanganate. Al, there's only one Al because it's not Al2 or Al3. Al, we don't even write the number 1. And then MnO4. Mn is something called manganese. It's kind of a cool element. Number 25. Yep, 25. And so there's 1 manganese and 4 oxygen. So in the parentheses, there's 5 atoms. 5 times 3, it's tripled. Aluminum, permanganate, permanganate, permanganate. That's the way it bonds. And we'll learn about bonding another day. But in this formula, you have 1 plus 5 times 3. That'll be 16. In the next one, ammonium carbonate. Ammonium is the NH4. 1 nitrogen and 4 hydrogens. That's 5. Doubled. 5 times 2 is 10. Plus 1 carbon. That's 11. Plus 3 more is 14 for the oxygen. The last one is called nickel Roman numeral 3 acetate. Now, this is a big formula. You know, C2H3O2 is the acetate part of it. There's only 1 nickel, and then we have 7 atoms in parentheses times 3. 7 times 3 is 21, plus the nickel, that's 22. So let's see what we got going on here. We got them all right. You should be able to do these, and you should be able to practice these, and there's more in the homework you're going to do. Now, there are 6 phase changes. We did this a couple days ago. You have to know them. 3 or 4 of them, you know for sure they're easy. One of them is not boiling because that doesn't include evaporation. It's the V word instead of boiling. And then 2 of them are hard. But you got to know them. Read my lips. You have to memorize these. You have to memorize them, okay? Solid to gas. I showed you the iodine. I heated it up in the vent over there. Turned into that purple gas. Solid to gas is called sublimation, or it's subliming. Liquid to gas, it could be boiling or it could be evaporation, or it's both. We call it vaporizing when a liquid becomes a gas. 1 phase change, it covers them both. Solid to liquid is melting. You can do that in your hand with chocolate or ice cubes. Gas to solid is the opposite of sublimation. That's the other hard one. That's called depositing or deposition. Liquid to solid, that happens when you put the water in the freezer, freezing, the F word. And then gas to liquid, that happens when you put your finger in front of a steam kettle and you cry. When you're crying, the steam gas is condensing into a liquid and releasing a lot of energy. Memorize these 6, please. Standard temperature. Haven't said this before. This is going to be a good, are you watching the Zooms thing? Because You're not going to get it otherwise. Here's my reference table. Look what it says right here in table A. Standard temperature. That's the official standard temperature. A lot of things happen at standard temperature. They just say standard temperature. You're supposed to know it. It's written right down. What is standard temperature? 273 Kelvin or 0 centigrade. I suppose 32 Fahrenheit, 32 degrees Fahrenheit, but we don't talk about that F word. We don't like that one. Kelvin or centigrade. 273 K, 0 centigrade. With the formula, what is the volume of 375 grams of sodium metal? So you know it's sodium. You need the volume. You got the mass. The density is in table S. And if you write the density formula, density equals mass over volume, you can go right to table S. Sodium is atom number 11. The density is 0.97 grams per centimeter cubed. So it'd be 0.97 grams per centimeter cubed equals 375 grams divided by volume. If to cross multiply, it's 0.97 grams per centimeter cubed times volume equals 375 grams. Divide both sides by the density to cancel the densities out. On the left, we get just V for volume. And on the right, the grams cancel and those centimeters cubed jump up to the numerator. And then with 3 significant figures, we have that answer. Now, you might ask, how come it's not just 2 significant figures? 0.97, 2 significant figures. No, no, no. That is a fact, Jack. That's from a table and not a measurement. It has unlimited significant figures. Our answer is limited by the 3 significant figures in the mass. Now, this is a giant balance equation, and you've not seen one of these before. I'm telling you what it is. Don't get all nervous. This is a balanced equation for what's called the combustion of heptane. Combustion is a type of chemical reaction where something burns with oxygen and turns into carbon dioxide and water. What's burning? Heptane. Let's look at the formula. C7H16, I don't know what the heck that is. We have 11 O2s, 11 oxygens, so that must be the oxygen. CO2, well, that's carbon dioxide, and you know this, H2O, that's water, so that must be the heptane. It combines with 11 oxygens. One of them combines with 11 of these, makes 7 of those and 8 of those. It's a big balanced chemical equation. Don't worry about it. Let's look at these questions. Of these 4 things, the C7H16, the O2s, the CO2, the H2Os, which of these 4 things are reactants? Which are the products? And then how many atoms are in heptane? Well, the products are in blue. They start the chemical reaction. The products are in red. The reactants are blue. I don't know if I said that right. The reactants are in blue. They start the reaction. The products are red. How many atoms in heptane? Well, the formula is C7H16. There's 7 carbons and 16 hydrogens, and 7 plus 16 is 23. All right. How do we separate mixtures? And what is that one line to remind us all the time how to do it? We have to take advantage of a difference in physical properties. Now, what are some of those physical properties? We could use a filter, take advantage of different sizes. We could use a magnet, take advantage of sometimes things are attracted to magnets and sometimes they're not. We could evaporate or boil away the water, right? We could just, one substance evaporates easy or boils at a low temperature, one doesn't. We could use a distillation apparatus and take advantage of a difference in boiling point. Chromatography, that's the picture I showed you, and I don't know if we did that yet, but we will use water to separate the colors of ink, and it will show different colors that are mixed together, and they will separate based upon whether they're soluble in water or not, or how dense they are, and they'll go for short rides or long rides in the water. We could use tweezers to take apart the iron and the sulfur. Iron is going to be a black metal, and the sulfur is a yellow powder. We could do that. It'd be slow, but we could do that. Take advantage of a difference in color, or we could melt them apart. We can use any physical properties that are actually different. Sometimes 2 things have the same boiling point or very close to the same boiling point, and it would be hard to control the heat so that only one would boil or another. If you have 2 liquids that are mixed together that happen to have very close boiling points, no, you might not be able to boil them apart. They might be too close. You might not be able to separate them out neatly and effectively because their boiling points are too close. You'll have to do it a different way. You have to take advantage of a difference in physical properties that's really a difference that you can deal with. Now, 4 boxes, A, B, C, D. Which box or boxes is a diatomic element? Which box or boxes is a mixture? Which box or box is a monoatomic element? Mono means one. And which box or boxes is a compound? Let's look it over. As it turns out, the only diatomic elements we have are in box B. Mixtures, we have no mixtures. In box A, we only have a compound. It's in a 1-to-1 ratio. Maybe it's sodium chloride. In box B, that's not a mixture. That's a diatomic element. It might be oxygens, pure. It's the same throughout. The next one seems to be in some sort of 2-to-2 ratio. Maybe it's hydrogen peroxide, H2O2. Well, that's not a mixture. They're all the same. And D, that seems like another element. Maybe it's neon, atoms of neon or atoms of helium, single atom gas, right? Maybe it's iron gas, but iron gas would be super duper hot. It's probably more something simple like a noble gas, simple atoms. So B is diatomic. There's no mixtures here. Monoatomic could be D, and a compound would be A or C because there's 2 or more different atoms bonded together. All right, my friends, that is the end of the slideshow for matter. You are now supposed to make sure you do matter homework number 1, matter homework number 2, and what's called the elements and matter handout. I'm going to ask you to cut the homeworks out, number 1 and number 2. They're on separate sheets. Cut them out. I want them on paper. Put your name on them. Do them in pencil. Do them neat and bring them to me. I'm going to grade them. Now, the elements and matter handout, that's still in the notes. You don't have to cut that out. I want you to do that. The answers are on the website, and we will talk about that another day. We also have a lab coming up. There's going to be one more lab called Chemical and Physical Changes Lab. I'm going to have to show that to you. I'm going to have to see about filming that, and I don't know how that's going to work, but that's coming soon. Hang in there. We're having a great time. All right, bye-bye. I never know how to turn this off. This is like the outtakes.